I'm Vivek Sarkar, glad to welcome you to this very specially thought out session on data management and concurrency. the first talk will be on the need for data management primitives in a VE by Jim Kleewein from IBM.
Hello. To start off with, whenever I give a talk, I like to state up front what my objectives are, what my success metrics are for my talk. So since I'm here as Johnny Appleseed and trying to plant a few ideas, my success metric is that if more than half of you either learn something new and have a new insight and don't fall asleep, then I will consider this a glowing success, whereas my idea of crushing failure is if anybody stages a fake fire alarm to leave my talk. I can safely say that to date, I have not failed utterly ever. I've never been involved in a fake fire alarm.
How about a real one?
Not a real one, but midway through a talk last year, we did have an earthquake in California.
And who faked that?
That one was a little bit harder to fake. Nobody got the entire building swaying, but so
someone high up was listening.
Somebody high up was listening to the prayers of somebody in the audience that day. So the basic message I'm trying to leave you with is there is actually a lot tighter synergy between systems than you might think. And as we look at the future for VEs, we should really consider data management a core part of that, and at least actively consider the inclusion of certain data management primitives and certain data management operations in a VE context. Okay. Now when we talk about database, a lot of people question the need for it. Main memory sizes are getting pretty honkin' big these days. If you want to buy high-end hardware, you can get hundreds of gigabytes in real memory these days, assuming you got a big enough puddle of cash. So why do we need databases anymore anyway? Because databases are really designed to handle environments where the data doesn't fit into memory by definition. And the simple fact of the matter is database sizes and the amount of data continues to grow at a substantial rate, primarily because we're making a lot of new data every day. 250 megabytes per person on the planet. So this is counting all the people in China and India and the guys in Africa who might not ever get near a machine. So for people in the U.S., it's a lot higher number than that. And as a consequence, the amount of data in databases and data managed repositories is continuing to grow. This is focused on structured data repositories.
This is 250 megabytes of information on servers, not on your personal machines.
That is correct. Okay. And this is only the structured data side of the house. So if you look, transactional databases, OLTP databases from 1999 to 2004 grew from where they were kind of in the double-digit, triple-digit gigabyte range to now having terabyte transactional databases is pretty common. I'm probably not a normal user, but I have a terabyte in my living room these days. So, don't you? That little, yeah. So I'm a slacker then. And transactional databases fail when you start to look at things like data warehouses, where transactional data warehouses are moving into the double and triple digit terabyte range these days. If we add in unstructured data repositories, the so-called content management systems, you add between 1 and 2 zeros to those numbers. We do have customers using our content management system where they have active repositories in the double-digit petabyte range. Those typically fall into two large classes of users. Number one is the government kind, and number two is typically media companies. So companies like CNN actually have monstrous collections because they digitize the snot out of everything. and then they want to index it and search for it, so that when Arnold Schwarzenegger is elected governor, I'm sorry for that, by the way, I didn't vote for him, they can immediately pull up all of the scandalous interviews of him in 1972 when he was groping people or whatever else he was doing at the time. So there continues to be a huge need for this. So where do databases and VEs overlap? Well, for those of you that have forgotten your database 101 stuff, when we look at databases, there are two big components: the clients and the servers. And I'm sorry if this is too complex for some of you. But what we're going to spend the next little bit of time doing is talking about databases and VEs. First in the context of servers, and then time permitting in the context of the clients. What is a modern database? For those of you that don't know, a database kernel is actually a VEE. If we look at a kernel of a product like DB2, it actually consists of a well-defined compiler component that produces as a result of it a execution in an intermediate bytecode language that's then executed by the runtime portion of the data engine. Okay, so the SQL compiler actually produces bytecode languages in a well-defined intermediate language. It's not a standardized one, so we can't take a DB2 compiler, stick it on top of an Oracle runtime engine. But it is actually 100% architected that way. And when I tell people about it, I always compare it to Java, because everybody understands Java compilers, bytecodes, runtime interpreters. You start talking to them about database, they glaze over. If you tie it back to Java, at least they follow a little longer. And if we look at some database implementations like Derby, the product formerly known as Cloudscape that we recently donated to Apache, it actually produces Java bytecode operators directly out of the SQL compiler. So the SQL compiler generates Java bytecodes that it then passes to a JVM along with some Derby class libraries, and away it goes. So a lot more synergy there than you would think. And it is a very specialized execution environment where the focus is, of course, on large-scale data manipulation operators, not on low-level flow control operators or comparison operators. So some of the bytecode operators we have are things like do a table scan, search through the whole bloody thing, and apply simple predicates, A equals 12, C equals 24, things like that. As a single operator pushed down to the execution environment, they'll do that. Similarly, there's index scan operators. Go search this index, return a list of ribs bounded by the certain range of values. And then you get into even more CISC-like bytecode operators, specifically designed at data manipulation and movement, like nested loop joins, merge sort joins, as bytecode operators in this environment. In addition, there's more normal stuff, flow of control stuff, branch on true, branch on false, unconditional branch, called subthread, comparison operators, data movement operators to move the data from the client domain into the database domain so that it can be actively worked on, as well as operators like sorting and temping. So that if we look at a simple SQL statement like select all the columns from A join B, where A is column 1 equal B is column 1 and A is column 2 equals some value in a host variable that's supplied at runtime, the bytecode operators look something like find the value of H1 from the client domain to the database domain, table scan A, applying the simple comparison of column C2 to whatever I bound in from H1, then do a hash join with B and bind the results back to the client. So if we look at internally what it looks like, this is from an internal serviceability tool. Customers would never see this, God willing, because if they did, it means it would be broken. But you actually see that it is in fact series of bytecode operators, flow of control and operations, and like any language, if you knew what the bytecode stand for, you can read it. Okay, so there.